Good morning, good afternoon, good evening. So we have now a new topic, and that is graphs. Okay. So in this chapter, you're going to learn the different terminologies about graph and how these graphs will be represented. And we're going to explore the two types of graph traversal. Okay, so we need to define what is a graph. So graph is a collection of nodes called vertices and a collection of line segments connecting pairs of vertices, which are called edges. Okay, and these graphs are normally used to represent networks and maps of roads, railways, airline routes, pipe systems, telephone lines, or in a prerequisite among courses, dependencies among tasks, manufacturing system, or electrical connections, and a host of other data. So there is a lot of applications of graph. And we have to determine the two different types of graph. So we have the digraph or directed graph and undirected graph. Okay. So when we say digraph or directed graph, it is a graph in which edge has a direction from the term, from the word itself, or from the term itself, directed graph, it has a direction. So every edge has a direction going towards its successor. Okay. So these edges are what we know are what we called arcs. Okay. And in this kind of graph, it should follow an indicated direction. Okay. So whatever or wherever the arrowhead points, then that is the direction of the graph. Okay. Well, when we say undirected graph, undirected means there is no direction, there is no arrowhead. Okay. So it is a graph in which there is no direction on any edges. Okay. So the flow will be between the two vertices. So it could go back and forth, or it could go either ways. Okay. Now, a traffic flow can be modeled by a graph. Okay. Now, each street's intersection represent also a vertex, and each street is an edge. Okay. So that is uh, how important or how significant graph is, especially in dealing with real life situations. Okay. So in here, we have an example of a directed and undirected graph. So for directed graph, as you have noticed, we have directions. We have arrowheads, okay? So we have an arrow pointing to whatever direction it is. So let us say I started from T, okay, from the T vertex, and then I'm going to go either ways. No, I could go to U or I could go to V. Okay, so if you would have a path, okay, path that is a series of edges, series of vertices that goes within the edges. Okay, so example, we have here from T, it goes towards to U, okay, from T to U, and then U to Y, and then Y to Z, or Z, okay? Or it could have another path from T, so from T going towards V, okay? And that's the end of it, because after V, it has a direction pointing to other vertex, okay? Or we could have another path from T, okay, from T to U to X, okay, and then to V, okay? So we have we have three different paths from vertex T. Okay. Ma'am, can we start at vertex U? Yes, you can. Okay. So you could have started from vertex U. So from U to X to V, okay? Or from U to Y to Z, okay? So that depends on the where's the start, where is the starting vertex, okay? Now for undirected graph, so undirected means there's no arrowheads. So that means it could go to and from. Okay. So in our case, in this diagram or in this graph, as you have noticed, it is like our first example, the directed graph. Now the difference is instead of having the arrowheads, no, it has no arrowheads. Okay, but the edges are the same. Okay, so if we will try to write all the paths from T, so we could have from T to U to X to V. Okay, so from T to U to X to V, and it could go back to T, right? Or it could end at V, right? Another is you could have from T to V, okay? So in this case, we have here from T to V, and then you could go to X, okay? Because there is no specific arrow, so it could go back and forth. So you could have after V, it could go to X, and then it could go to U, okay? And it could go to Y, and it could go to Z. Okay? Or another is from T, okay? So from T, it could go to U, to Y, to Z, right? Just this one, just like this one. So we have T, U, Y, Z, okay? Or it could have um, a cycle, no? It could have from T to U to X, and then go back to U to Y to Z. So it could go that way, okay? So we could have from T to U to X, and then from X, it could go back to U, and then to Y to Z, okay? So that is how undirected graph works, okay? All right. So let's define each term. Okay. So we have adjacent vertices. When we say adjacent vertices, there are two vertices which uh, or two vertices which is connected by an edge. So that means we could have it called as the neighbor. Okay. So let's have adjacent vertices are T and U. Okay, they are connected by an edge. This one is their edge. Okay, so that is one. That is an adjacent. Okay, what else? So adjacent vertices are T and U. Okay, another set of adjacent are U and X. Okay, how about T and V? Are they adjacent? All right. So from V to T, they are still connected. How about T and W? Are they connected? Are they adjacent? Very good. Okay. No, they are not adjacent. There is no edge connecting vertex T and vertex W. Therefore, they are not, they are not adjacent. Okay. Is X and Y adjacent? Very good. They are not adjacent because X and even Y has no connection between them. Right? There's no edge between them. Okay? So, yeah. Another adjacent vertex is B, W, W, and Y. Right? Next, when we say path, okay, let me first, yeah. So when we say path, that is a sequence of vertices in which each vertex is adjacent to the next one. So that means we could have a path. Okay, so we could have B to T to U to X. That could be one path. Okay? We have from B to T to U to X. So we have one path. Another path would be, it could be from B, okay, to W to Y. Okay? That would be another path, right? Or we could have another path from T to U to X. Okay? Or you could have a path from U to X. Okay? Or you could have another path from W to Y. Or another path from B to W. Right? So this is how path works. Next, when we say cycle, so cycle means it is a path consisting of at least three vertices that starts and ends with the same vertex. Right? It starts and ends with the same vertex. Okay, in our given example, do we have a cycle? Minimum of three vertices. Okay, so do we have here a cycle? Let's have from T to U to X. Wala, no? It doesn't start and ends on the same vertex. Okay? From V to T to U to X, still, it has no path. I mean, it has no cycle. Okay? Because it doesn't start and ends with the same vertex. It starts with V, but it could end with T, or it could end with U, or it could end with X. Okay? It could end with U. No, I'm just kidding. All right. Next, loop is a special case of cycle in which it has only a single arc that starts and ends with the same vertex. Here, okay, we have here an example, another example here, okay, of a loop. Okay, as you have noticed, we have X and it has an edge that starts and ends with the same vertex. So we call that as a loop. Okay, so possible that in this graph, it could have a loop. It could have more than one loop. Sorry for the arrow. Okay. Yeah. Right. Next, when we say strongly connected graph, okay, it is a directed graph or digraph, which has a path from each vertex to every other vertex in the digraph. Okay. While when we say weakly connected graph, this is a digraph also which has at least two vertices connected. Okay? Take note that a connected undirected graph would always be a strongly connected graph. Right? Again, connected undirected graph will always be a strongly connected graph. Okay? And when we say disjoint, it is a graph that is not connected. Okay? Um, Degree of a vertex, that is the number of lines attached to that vertex. Out degree, it is in a digraph, it is the number of edges leaving the vertex. And in degree, it is the number of edges entering the vertex. Okay. So let us have this example, no? So again, when we say strongly connected graph, it is a directed graph. Strongly connected, it is directed graph, so it has arrows, okay, which has a path from each vertex, okay, to every other vertex in the digraph. Okay, so every vertex has a connection with other vertices. Okay, so if that is the case and it has a path from each vertex to every vertex, okay, so like we have T to U to X, or it could have from W to U to X, or it could have from W to X, or T to V to W, or T, V, W, U, X. Then, as you have noticed, every vertex are connected via their edges. So this is an example of a strongly connected graph. Okay. Well, when we say weakly connected graph, okay, it has at least two vertices connected. Okay, minimum of two vertices that are connected. Okay, and then um, notice that vertex Y has no connection with other vertices. Okay, um, W has connection with Y, but Y has no connection with other vertices. Therefore, this is an example of a weakly connected graph. Okay, while this joint, okay, when we say this joint, this is a graph. Okay, if that graph have a graph here, okay, that are not connected, right? So as you have noticed, um, V V graph is not connected with T and W graph. Okay, so this is an example of a disjoint. Okay, moving forward. Okay, so we have now degree of a vertex, out degree, and in degree. So when we say degree of a vertex, it is the number of lines attached to that vertex. Okay, so let's say we have vertex T. So we have vertex T. What is the degree of vertex T? Okay, all the lines that are connected to T. So it's either leaving the vertex, so T leaving the vertex, this one is an edge leaving the vertex, and this one is another edge that is leaving the vertex. So we have two vertices leaving that vertex, okay? Let us say U. Okay. How about degree of vertex U? Okay. So degree of vertex U is one. We have, okay, U as a vertex. Okay. The line that is leaving, or an edge that is leaving that vertex, is this one. Okay. While another edge entering to that vertex is this one. Okay. So we have two edges. Okay. Therefore, we have two. Okay. Uh, Di pala? Okay. Next, let's say we have degree of W. Okay. Degree of W, again, we have two edges connected to that vertex, either leaving or entering. So we have two. Okay. Degree of vertex X. Okay. Vertex X has two edges entering that vertex. So again, it is two. How about V? Okay. Vertex V has two edges. Okay? We have entering it and leaving it. Okay? So we have 2 degree of vertex V. Okay? But when we say out degree, out, ibig sabihin, okay, that is the number of edges leaving that vertex. Okay? So let's say degree of, out degree of vertex T. Okay? Out degree of vertex T, how many? Okay, we have 2. Okay? Out degree of U. U, how many out degree? Very good. It has only 1. Okay? W, how many out degree? All right. So W has only 1 out degree. Okay? X, on the other hand, how many out degree? Very good. There is none. There is no edge leaving that vertex. Therefore, it is 0. Okay? Next, how about V? Okay? So, very good. We have only one vertex leaving that, one edge leaving that vertex. Okay? On the other hand, when we say in degree, in, that is incoming to that vertex. Okay? So let's say in degree of t. Okay? How many edges are entering that vertex? So t, how many edges entering that vertex? Very good. There is no one. Huh? So we have 0. What it has are only out degree. Okay? How about you? U. Okay? So U has only 1 in degree. W also has only 1 in degree. X, on the other hand, has 2 in degrees. Okay? Has 2 edges going or entering towards that vertex. Okay? While V, how many edge? Very good. It has only 1. Okay? So notice, if we're going to add the out degree and the in degree, that will be the degree of the vertex. Okay? So for vertex T, 2 plus 0 is 2. So that is the degree of vertex T. U, out degree and in degree, so we have 2. So U has also 2 degree of that vertex. For W, 1 plus 1 is 2. Again, the degree of our vertex is 2. Okay? X has 0 out degree and 2 in degree. Therefore, in total, it has a degree of 2, which is true, right? X has a degree of 2. Okay. Next, how about V? We have 1 out degree and 1 in degree. Therefore, we have 2. Again, we have 2 degrees of that vertex. Okay. Moving on, we have now graph representations. Okay. So there are 2 ways to represent graph, just like the other topics that we have. Okay. So it could be represented using an array. Okay, an array or a matrix, or it could be using a linked list. Okay, so here we have a graph. This one is an undirected graph. Okay, and then if we're going to draw the adjacency matrix for this one, okay, all we have to do is write a value of 1 if it has an edge connecting to that vertex. Otherwise, write 0. Okay, so let's start from A. Okay, this is how you create the matrix. Okay, so it's like a 2-dimensional array. okay, a two-dimensional table consisting of the rows. Okay, we have 1, 2, 3, 4, 5 rows because we have 5 vertices. Okay, and you have to arrange the vertex alphabetically. So we have A, B, C, D, E, A, B, C, D, E, right? Same true with the columns. Okay, so you're going to write each column, okay, with each column heading of their vertices. Okay, so from A, okay, from A to A, from A to A, do we have an edge from A to A? None. So that will be 0. From A to B, it has an edge? Yes. So that will be 1. Okay? From A to C, from A to C. All right. There is no direct connection, therefore it should have a value 0. Okay? Next, from A to D. So that has the value of 1 because it has a connection. It has an edge. Okay? From A to E. There's no connection. There's no edge. Therefore, it is 0. Okay? Moving on. From B. Okay? Let me... yeah. From B. Okay? Now, another technique is to simply look at the lines, okay? So B has an edge to A, okay? So from B to A, and it has also an edge to D, and it has also an edge to C. So just write 1, 1, 1, and then the rest are 0. One more, okay? From C, there are 2 lines, right? There are 2 edges. Okay, so these are the 2 edges. Okay, now those 2 edges. Okay, and so it goes towards B and D. Therefore, you simply have to write 1 to the vertex B and D. And then the rest are zeros. Okay, from D. All right, from D. So from D, it has edge here going towards A, B, C, and E. Therefore, you simply write 1, value 1 to A, B, C, and E. The rest, 0. Okay? Next, from E. Okay? From E, this one, going towards, it has only a line or an edge going towards D, right? Okay. So it has only one line going towards D. Therefore, D has a value of 1. Okay? And the rest, it would only have a value of 0. Okay? So we have now created the adjacency matrix for this graph. Okay? Let's have another example. Okay, let's have another example. This time, let us have a directed graph or digraph. Okay, so we have here directed graph, same graph a while ago. However, the previous one is undirected graph. So in this case, we have here directions. Okay, we have arrowheads. Okay, that would simply specify the direction of the path. Okay, so let's draw its adjacency matrix. So from A, okay, all you have to do is to check all the edges from A going towards another vertex. Okay, so same way of drawing the table. Okay, so from A, it has a directed line or edge going towards B and D. Okay, so B and D. The rest are 0. Okay, while from B, okay, from here, from B, it has only an edge going towards C. Okay, outward. So out degree. You're going to look for the out degree from the vertex. Okay. So we have only one out degree from B that is going towards C. So B to C. How about these two? Okay. They are not considered as an adjacency, right? Remember, adjacent vertices are those that have connection from that vertex, okay, to another vertex. So in this case, it has only an edge from B to C. The rest are 0. Okay. While from C, okay, it has an edge going towards D. So D. And the rest are zeros. From D. While from D, okay, from D we have edges going towards B and E. So we have B and E. The rest are zeros. Okay? And last, from E. From E. Does it have out degree? Very good, none. Therefore, all of these are zeros. Okay? So that's the difference between an undirected graph and directed graph. For undirected graph, all the lines, no, are considered as adjacent vertex to that vertex or adjacent edge. While for the directed graph, you should look for the out degree. Okay? Another way to represent is using linked list. Okay? So how are we going to represent using linked list? We have here an example. No? We have vertex 0, 1, 2, and 3. All you have to do is to specify all the vertices. So vertex 1, 0, 1, vertex 2, vertex 3. Okay? So from vertex 0, you simply draw the node. Okay? From vertex 0, it goes to vertex 1. Okay? And then from vertex 1, it has a loop to itself. So it goes again to 1. And it could end there. That's why it has an X. Okay? Or another path would be from 0 going towards 1. Okay? And then from 1 going towards, okay, from 1 going towards 3. Okay? And then from 3 going towards 2. And then from 2, it has no edge going towards anywhere. So that would be the end of this vertex. Okay? Or it could have a loop after from 0 to 1, another 1, another 1, another 1, then 3, then 2. So it could have that way. Or another one is from vertex 0 going towards vertex 0 going towards vertex 2. Okay? And that's it. While vertex 1, it could have from 1 to 1, okay, to 1 again, or it could have only one iteration and then two iterations rather, and then it could have 3. Okay? And it could end at 3, or it could end at 2. Okay? So we could have several paths on this. Okay? And then 2 2 vertex 2 on the other hand, it has no edge going towards anywhere. Therefore, from 2, it has now the X or the null. Okay? And then from vertex 3 going towards vertex 2, and then no more, so that would be X. Okay? So this is how we represent graph using linked list. Okay? All right, so we have now graph traversal. So when we say graph traversal, that means we're going to visit each node or we're going to visit each vertex, okay? So this vertex could be processed only once, and there are two types of graph traversal that we could use in graph. So we could have the depth first traversal and the breadth first traversal. So when we say depth first traversal, that means all the vertex descendants are processed before we move to an adjacent vertex. It is just like a pre-ordered traversal in a tree. It is just that in graphs, okay, we could have more than two um, branches rather. Okay. So as you have noticed here from J, it has three edges going towards K, L, and M. Okay. And then from K, it has an edge going towards N and O, while M, it has an edge going towards P, Q, and R. Okay. So going back with the definition of the depth first traversal, that means we're going to process first all the vertex descendants. So that means from here, okay, it's just like a pre-ordered traversal. No, we follow from this one, from the first vertex. Okay, so we process the first vertex and then go to the descendant. Descendant of J is K, and the descendant of K is N. Okay, another descendant of K is O. So we're done with this. Okay, go back here. Another descendant of J is L. And then no more other vertices here. Therefore, let's go to another edge going towards the vertex M. So this is the descendant. Okay, so M. And then M has descendant P, Q, and R. So we will do it from left to right manner. Okay. So just like the pre-order, okay? It's like you're going to process first the root, okay? And then left, right, okay? And then the center, and then root, left, right. Root, left, center, and then right. Okay? Next. While the breadth first traversal, the manner in which it is traversed is all the adjacent vertices of a graph are processed before going to the next level. So that means each vertex within that level will be processed first before going to another level. Okay, so let's have the same graph that we have a while ago. Okay, so in this kind of graph, it is on three levels. So at level 0, level 1, and level 2. Okay, so we're going to process by level again from left to right. Okay, so J will be processed first, and then next level we have KLM. So J, K, L, M, and then go towards another level. Next level is level 2. It has these nodes from N, O, P, Q, and R. Right? So this is much easier than the first. But of course, it is easier for you because we are done with those pre-ordered traversal of the tree. Okay? So that ends my discussion. That ends our topic for graph. So let's have this another example for you to do with your assessment. Okay, so find all nodes adjacent to node E. So let's have only this one, no? Let's try to answer this one. The rest you'll be answering the other problems. Okay, So all nodes that are adjacent to E. So this is the vertex E, this is the node E, and then adjacent to it are, okay, since this is an undirected graph, so all the edges that has connection to that vertex, so that could be an adjacent to that vertex. So we have here from E, adjacent shape C, adjacent to F, as well as adjacent to G. Okay, so you find adjacent to D. Okay, so what vertices are adjacent to D? Very good. Adjacent to A. Very good. And then find the degree, out degree, and in degree of the vertices A, E, F, G, and H. Okay. So let's have first the A. Okay. And then the rest we're going to answer that. So degree of A. All right. Degree of A we have two. Out degree of A. Out degree 2. Very good. And in degree of A. In. Okay. Again 2. So which means, why is it there are all 2? Remember, in an undirected graph, the direction could be to and fro. Okay, so it could uh, go towards that vertex, or it could leave that vertex. Okay, so that's why it has always a value of 2. Okay, definitely that would be for directed graph, definitely you would have different values for the degree, out degree. Okay, so I'll just leave it to you, the answers for E, F, G, and H. Okay, and lastly, you're going to give the adjacency matrix for this kind of graph. Okay, so you have to draw the table. Rows are A, B, C, D, E, F, G, H. Columns are A, B, C, D, E, F, G, H. 2. Okay, and then write 1 if there is an edge connecting that vertex. Otherwise, write 0. Okay. Another is for this one. No? Given the adjacency matrix, so let's do the other way around. Given the adjacency matrix, you're going to draw the directed graph. Okay. So from you're going to first you're going to draw the vertices. Okay, so you have vertex A, let's say we have B, we have C, D, E, and F. Okay, and then okay, I'll answer number 1. I mean the first row. Okay, so from A to A is 0. From A to B, it has 1. So from A to B, it has a direction. So there is an arrow. This is a directed graph, so I must have an arrow. Okay. And then from A to C, again, it has an edge. So there is a direction from A to C. Okay. And then from A to D is 0, so there's no connection. From A to E, it has a connection. So from A to E, it has a connection. And then from A to F, it also has a connection. So there is a line going towards A to F. Okay? And then you're going to draw the other. Okay? This is D, huh? Okay. Question? So just send me a message if you have a question on this. Okay? So that ends even the assessment. Thank you and God bless.